Now we are going to talk about more about programming language class itself. So, not the programming language itself. Why people try to learn programming language course in a computer science curriculum. The programming language course is not about running specific programming languages. For example, Python, C, C++ are probably taught in elsewhere. There are other classes, other courses. The focus of the programming language course is try to understand the common principles across all programming languages, and also try to learn how those high-level features are implemented behind the scene. So it's more about the compiling the high-level languages or compiling program languages. So to come to the program language course, you have to also build some of the experience with the basic programming skill in elsewhere, the other courses. So you have to know about the script languages, for example, Python, and C, C++, Java. Probably you can have chance to run it in another program language or by yourself. Also, we have the many lab exercises, and then in that lab exercise, they try to use the specific program languages. So you have to build your experience in programming with those languages. And also in the CS course, they used to have the project work. So you have plenty of chance to build your experience in the programming. So actually, we talk about what we are going to learn in the programming language course. I'm going to start with this. So there has been the American TV series called Heroes. It's been probably 2000, the middle of 2000, and up to probably 5 seasons. So one of the character in that drama is a sailor. He is also called the watchmaker, because he got some of the superpower. So, but his own superpower is he can observe other heroes' powers. So later on, at the end of the series, he can observe 18 different powers from several heroes. So how they then what's the superpower of his? Let's actually try to understand how things work. He started his career with a watchmaker, so and then he actually fascinated by the mechanical watch movement and how they interact. Those mechanical parts interact and then make the actual watch as functioning, and then based on that, he obsessed with the understand how things work, including how superpowers works. So he's the probably the I mean there has been many heroes in that drama, but actually he was the most interesting the superheroes in that drama. So why I'm telling this? Because the programming languages are then not only the programming languages, probably the basic course in the computer science curriculum. Let's actually try to understand actually how computer works, how programs actually works. We want to understand it, and then based on that, we can develop more high-level 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 technical parts of the computer science. Okay, so before we talk about the high-level things, machine learning, computer graphics, and then data processing, big data, we want to understand how actually computer works, how actually the program works on the computer. Okay, that's probably the basic goal of this this course. Okay. Okay. The first, I'm going to try to explain how actually program runs on a computer. So we know that the computers are, and then probably the main part of the computer is going to be processor, CPU. And then the processor itself, it's actually manufactured with the semiconductors, right? You know the semiconductors, right? So semiconductor means we actually developed this transistor from the semiconductor technology, and then it's been called MOSFET. Probably if you take the other courses, for example, electronic circuits, then you will understand what's MOSFET and then what's the transistor. But in here, the transistor, what we want is transistor. The function of the transistor, it's actually switches in a digital logic. I'm going to talk starting from the digital logic. Below that, probably not the part of the computer science. Probably if you go to the electric engineering department, then they will talk about this more in detail. But in computer science, we start with the digital logic. So, but if you look at the digital logic, it actually has many logic gates. For example, AND gate, OR gate, and then NOT gate, and there are more, right? And then those logic gates are actually constructed using transistor. Okay. Here's some of the example here. So I have actually two transistors, T1 and then T2. You know the basic of the transistor. So it actually this is the high voltages, voltages here. For example, in a computer, it's usually 5 volt, right? And then this is ground, it's 0 volt. So the current will flow in this way. So that means the electrons flows in different way, right? So if you look at these switches, I have two inputs, A and B, so I can just make it 0 voltages or 5 voltages. 5 means 1, and then 0 voltage means 0 in logic. So if I have 1, then I'm going to turn on these switches. So I can have the current flows, okay? If I turn on 1, I can have turn on the switches here. So it will turn on to the here. So if I just select the voltages from this, then this is 5 voltages here, and then because there is registers here, if it's been turned on by setting 1 and 1, then I'm going to have the 0 voltages because it is grounded. So they are going to be the same voltage level, and then 5s are here, and then because of this register, it's going to be consume those currents, and then becomes the 5 voltages there, right? So I'm going to be this 0 voltage out here. So if it's 1, 1, only that time I'm going to get zeros. That's the logic, right? If it's all turned on, B and A is turned on, then I'm going to get 0 voltage there because this current just connected, so I'm going to get 0 voltage there. But otherwise, only 1 is turned on, or all is zeros, then I don't get any current. So it's going to be the same as this voltages. They are going to be 5 volt. So I'm going to get the output 1. So this is the actually in a logic gate. It's the same as NAND. So NAND means actually AND plus NOT gate, just that they are combined together. So NAND means only if I have 1 and 1, because it's AND. So I'm going to produce 1 here, but I'm going through the NOT gate, so the result is going to be 0. So only when 2 inputs are 1, I'm going to get 0. Otherwise, everything is 1. So that's the NAND gate in a logic circuit. And then actually NAND gate is the universal operators. If you take the digital systems, then you will run this. So using NAND gate, you can actually implement all the other logic gate. For example, AND, then OR, and then NOT. You can implement it by using this. You can easily imagine it, right? You can imagine it. And then that's why we call it, this is universal gate. So if you just build the logic circuit with a NAND switch, NAND gates, then you can imagine that I can implement it in a circuit like this, in a circuit with the transistors. I can just turn into them into the transistor, and then I can actually implement it in a semiconductor level. Okay. So we are starting with the logic circuit for a computer. And then now we are going to move to the more high level, the functions out of this logic circuit, logic gate. In this slide, we try to implement adders. Okay, 1 bit per adder, meaning I can have 2 inputs from A and B. So all possible combinations are 0, 0, 1, 0, 1, 1, 1, and 1, 0. That's all possible combinations. And then also I have the carries, okay? Because it's a 1-bit adder, I can have like multiple positions in the numbering systems. Then when I just try to add it, for example, I can just add multiple bits here. For example, I have 3 bits, okay, 4 bits. For example, I'm not sure I'm doing right, but when I'm doing this, when I add it, I can just add these two, right? I can add it, right? I can add this, but 1, 1, make 0, and then make a carry, right? Carry to the 1. That's the carry, okay? So I'm just trying to focus on the 1-bit adders with the carries, okay? So this is A, this is going to be B, and then this is the carry, okay? So I have 3 inputs, and then I'm going to make the result, okay? This is all possible 8 different results because I have the I have these 3 combinations, and then out of this I'm going to have the sum of this bit, and then I'm going to have the next carry if I have it, okay, to the next position. So I'm going to have the carry here. That's the output. So here is the logic for out of this truth table. So I'm going to have the A and B and carry in. Based on this, I can have the sum and then carry out to the next position. I can implement this. So I don't want to expand. I don't want to spend more time on how to implement this, but if you take the digital systems, they will tell you how to change how to translate this truth table into the digital logic. So if you look at here, I'm only using NAND gate that's been in the previous slide. So you can implement it in a semiconductor transistor. So I can implement adder with this. Okay. So if you wanna, for example, 4-bit adders, so I can have, this is 1-bit per adder. Okay. So I can have 4 of them for each bit. Okay. So the 4 bits from 0 to 3. So I have the 1-bit per adder here. I'm going to get the result of the sum, and then probably I can get them carry in here and then carry out to the next position. So if I build this in this way, then I can build the full bit adder, the higher bit adders. Okay, so if I need 32-bit adders, then I can have this 32 of this. Probably it will take time to propagate carriage, right? But once you just propagate all of them, and then it will be stabilized there, and then I can get the result. So I have adder here. Now we are going to build the actual computers out of this. Okay, this is the typical 5-stage pipeline computer architectures. Within here, there is ALU here. This is the actually arithmetic logical unit. So it provides several functionality in arithmetic, add, subtract, for example, multiply, and then divide. You can implement those functionality using logic circuit we just built in the previous slide. We just built the adders, but you can build it for different functionality in that way. And then also you can implement the logical operations and or not those operations. So you can provide ALU here. And then there's several the blocks here, right? So it's been it's actually the memory blocks. So you can store something there, and then store something there, and then use it later. This is registered in the computer architecture. You can just write back into the memory once you have the older computations, and then you can also write back to the memory, or sometimes you can just read from the memory, and then store them into the register sometimes. So you have the pipeline computer architecture here, and then they all represent with the block diagram. And then inside the block diagram, you can have actual digital logic there. So you can implement it as if they are the full bit, the full 4-bit adders in the previous case. And then if you understand these architectures, and then you will also understand, if you look at the program in assembly languages, actually it's like 1 and 0s, and then the stream of those things. So if you look at the actual instruction stream, I just wrote it in a hexadecimal code, so it's 16 bits, okay? But if you look at in a binary numbers, then it's going to be 1010, right? So I have a stream of the instructions, and then if you look at more specifically, and then I can just group them in a certain way, then they make the actual instructions. The first one is move instructions, then add instructions, and then exclusive or push, move, and then load effective address, and then compare, and then jump not equal, okay, and then return. There are instructions there, and then these AX, BX, and then those are actually register files, okay. So I can have some of the meaningful work by having assembly languages here, and then that's actually in a binary executable code, they are like 1010. I just wrote in a hexadecimal numbers, but they are 1010. And then I just getting these instructions one by one, then they can go through this 5-stage pipeline, and then they are going to be executed, okay? So up to this point, and it's to we understand. So we have the instructions, and then we know how they are encoded, to either represent the move. I can, for example, use some of the encodings there for representing move instructions, and then representing these numbers, right? These numbers here, and then store them into the AX. Okay. So getting this encoded, I can just interpret it here, decode it, and then actually execute it. Okay. Move this constant to the AS. So I can just write back to the razor file, write back stages, and so on. So I can just run each instructions. So if programs are implemented in assembly languages, we can run it on a computer, and then that computer actually designed with the logic blocks, and then inside the logic blocks you can see the logic circuits, and then those logic circuits you can also implement with the actual transistors. Okay, that's how computers actually works. And then the early days, once computers are built, and then people try to program it with assembly languages, because that's the only thing you can have to program. But in these days, probably assembly language are probably the last choice to program the computer, because it's time consuming, and then sometimes you can make it, it's hard to make it correct programming and hard to debug it. Okay, so only very few module, very core module, that if you actually learn in a fast way, in an optimized way, then people probably try to build it with assembly languages. But other than that, most of the programming are implemented in high-level languages. And then now we have to understand how people write the high-level languages, and then they can be translated into the assembly language level, actually machine level languages. That's the probably the final part, or the topics we in the programming language course want to talk about. Okay, so as I mentioned it, this is going to be the last puzzle, how high-level programming languages are actually translated into the assembly code, actually machine code, because assembly code itself is actually one-to-one mapping to the machine code. So for that function, we are going to have the compiler. Okay, and then if you have the many programming project in a C, then probably you already know the GCC, GNU-C compiler. Okay, the role of the compiler is actually getting source code, and then you just analyze source code and then make it into the intermediate representation, and then using intermediate representation, you do the sum of the optimization on this representation, and then finally you are going to get binary code there. Okay, for example, I'm going to have the high-level programming, high-level program language written in high-level program language. That's actually C. So I'm going to just write the add functions, getting argument to A, then just add 1 to the A, and then return A, right to the caller. Okay, and so once you just write the high-level program like this, the compiler will analyze it and then change them to the intermediate representation called IR. Okay, so actually the intermediate representation should have all the information you can get from the source code. So here's probably the intermediate representation itself, some of the structures in the program, but this is just a human readable representation of the intermediate IR. Okay, so I'm going to define the function name is add. So it's the same as add, but I just put the alpha here so that I can just compiler just understand this is the name of the function, not just the variable. Okay, and then for the variable, I can just put the percent symbol in front of it. So %A means the variable A, and then for that thing, I always put the types in front of it. So this one is going to be integer, and then the size of this is 64-bit integer. Okay. And then the return type also int. I'm going to have the 64-bit integers as a return type. And then this is the label entry, the function body here. And then I'm going to introduce temporary variable t. So %t is the variable. And then those a, I'm going to add one constant one to this. And then to this, I also have the types of this. Add to the variable a, and then result has been stored in the temporary variable, and then the type of this is also same as integer 64-bit, and then I'm going to return it. That's the intermediate representation, the internal form used by compiler. So just analyze it, and then I can produce intermediate representation like this. And then based on this, I'm going to produce, make assembly code, produce assembly code like this. Probably you can just, if you can just produce the assembly code, you can directly produce the machine code too. But in here, to understand more easily, this is human readable form of the machine code 1010 here. And then if you just interpret it in an assembly code level, then it's going to be something like this. So I'm going to label add, that's the starting point of the function. And then this push and move and then pop as the just prologue code of the function and the epilogue code of the function. So every time you just run the certain functions, you need some of the space in the stack. So this is for allocating those space, and then setting up the base pointers and then stack point based on that. Okay. So and then these three codes are actually the statement that match to the IR here. I'm going to access the based on the BP. This is register, and then this is offset from there. Then I'm going to access the because arguments are stored in the stack, so I can just access that argument here A, and then getting that value and then store them into the into this registers, for example, and then I can just add them, add one to this address, okay, this address, this memory locations, stack locations, and then the result will be stored in the return address. I mean return result, because in the Intel architectures, you can just return the return value through the AX registers. I can just return it. So probably you don't have to focus on the meaning of the statement. But try to focus on the role of the compiler. Getting high-level languages here, and then analyze and then translate into the intermediate representation. And then out of this intermediate representation, you can just generate the assembly code like this, and then you can just turn them into 1010 final machine code there. That's the role of the compiler, and then that's once you have it, then you can just execute it on a computer, pipeline computers, or the logic blocks we've seen in the previous slide. Okay. So what we are going to learn in the program languages first from language course the first topics of the programming course, it's going to be compiler. But the traditionally compilers are two-pass compiler. It's called two-pass, front-end and then back-end. So you are going to have the source code written in high-level languages and then pass through the front-end. This is some of the computational module. It actually program. Getting source code and then pass through the front-end, and then you are going to get intermediate representation. So once you have intermediate representation, actually between them, actually there is mid-range to optimize it. But to make it simple, so we just leave out the mid-range. So intermediate representation here is going to be fed to the back-end program. It's actually program. So back to the back-end, then you generate the machine code, assembly code and machine code there. Okay. So the role of the compiler in a high level, it try to recognize legal program, because we have to write the program in a high level language. Sometimes the grammar is not correct, or the format is not correct. So you have to recognize this is legal program without any errors, without those grammatical errors. And then once you know that this is legal program, then you can generate correct code. So that can be suitable to the specific operating system, and then also specific linker they provide. So that you can just combine multiple object files into the one, and then also you can just load it into the memory so that you can run it. Okay. And also, this is probably only the statement, or only the instruction level, machine code level, but also you have to manage all the storage of the variables, and then where you are going to put those variables in the specific address in a process, because all the processes we are going to have the virtual address space. So I'm going to put that in that space. And then you also have some of the code to get those data and then store those data in the right places. So two passes, we mentioned the front end, the back end. So front end actually look at the grammar. So it's actually try to the legal source code into the intermediate representations. So while you are mapping, you can just discover some of the errors, grammar errors, then you can just raise it and then report back to the programmers so that they can change the high-level programming languages, right? The source code written in high-level programming languages. And then backend maps IR into the target machine code. So we have the target, Intel or ARM, depending on different architectures, we are going to get different machine code, right? So backend take care of the binary code generations. So between them, we are going to use the intermediate representation. Okay. So I can have multiple front end, multiple probably the back end, multiple passes. Okay. So because front end take care of the grammar, so I can have C front end, I can have Java front end, I can have Python front end, for example. The Python is not compiled languages, but assuming that it's one of them, then I can have the front end, right, to take care of different grammars in the different programming languages. And then back end to take care of the different machines. I can have Intel x86 machine, I can have ARM machine, I can have MIPS, I can have RISC-V, different machines there. So backend will have different generation model for different machines. But in the compiler, usually the IR is the common part. So everything is compiled into, analyzed into the same IR, and the same IR is generates the different machine code. So I can just combine them, write high-level language front-end, right? Machine code generation backend, then I can handle all the languages. I can handle all the process machines, right? After we see the compilers, the second topic in the programming languages, we try to understand the several fancy features in the programming languages. For example, programming languages provide object-oriented concept, so class hierarchy, virtual functions, and then if you have some of the experience in the programming language itself, the actual programming language, I mean C++ or Java and Python, they provide this, and then we want to understand how they can be implemented. Also, we also want to know the runtime memory management, for example, garbage collections. So, for example, we mentioned it in a Java programming languages, we can just allocate it, but we don't have to pre. Pre is going to be handled by the garbage collection module in the Java virtual machines. And then we want to know how those features are possible and how we can actually implement it. So this is the some example program written in C++. So if you look at here, I have two classes, class A and class B. And then the class B, actually the child class of class A. So class A is parent class and class B is child class. So we have a hierarchy. A is above here and then B is there. So if you have class hierarchy in a programming languages, you can just inherit anything from the parent to the child, and then you can modify a little bit in a child level, or you can add different functionality or different parameters in the child. But if you look at here, A has only one method called F, and then it's going to be just print out A. Okay. And then if you just inherit the parent method F, it's going to be the same. But in here, we decide to change it. We decide to modify the parent method F. Instead of having F function itself, we decide to change it so that it can just print B. So any class object A, any object of the class A type object will print out A. Any class object type B will print out B. Okay, so depending on object type, it's going to be we are going to call the same method F, but object of A type will print out A. Object of B type will print B. Okay, so here's the function G here. So within G, actually G is called in main function. So the G is probably the only function it's going to be executed here. So I'm going to allocate B type object, new B, okay, B type object, and then assign to the pointer. And then here I'm going to have the reference type of A. So I'm not going to allocate the object. I have just reference variable here. So I'm going to copy the pointer, copy the pointer of the B to the A. So actually the A and BP actually pointing to the same object here, right? So BP is going to be pointing B object, B type object, okay? It's allocated here, and then BP is pointing to this. I'm just copy that one to the A. So reference A is also referencing same type object. Okay, it's alias actually. So within this situation, so we are going to call, using BP, going to call F, okay, method F, here, which one? So BP is actually, BP is type is B, so if you are calling F, so this is going to be called, and then probably they'll print out B, right? How about this one, A? A is A-type reference. So if you are calling method F using this type reference, A-type reference, will it call this method and print out A? Or because A is pointing to the B-type object, the reference A is type is A actually, but the object itself is B-type. So should we print out, because this is B-type, object is B-type, should we print out B? The actual C++ syntax says that this is going to be this. It will print out B because this F function is virtual. So we mentioned that this is virtual, this is virtual. So it doesn't matter the type of A. It actually matters what type of object you are pointing to. So that's B type. So I'm going to call B type method F. So it will print out B. That's the definition of the virtual function. If you just take out virtual here, you don't specify, if you don't specify the virtual, so take out the virtual, then it's going to be normal function, not the virtual function. Then you are going to get B and A because it's not virtual function. The function F actually decide by the type of A, reference A, because this is A type reference. So I don't care whether I'm going to pointing B type or A type. This is I'm just A type reference. So when I call F, I'm going to call A class A is F. So it's going to be print out A. This one is B, and then this one is A in that case. But if you have the virtual, then it's going to be B and B. That's the syntax of the virtual function. And then we want to know how they are going to be implemented. We want to know that. And also, I just allocated B here, right? Then it's going to be allocated in the heap, and then I just store the address of the object B in here and here. I have two storage places that contains the A, and that contains the address of B. But when I just coming back from the G and then come to the main function after executing the G, I just return from the G here. No one actually free the space for object B. Then how can he access those objects? Because we don't know the address. The address are stored in BP and A, and that's actually local variable of G. So once you return from the G, those local variables are gone. So we don't have any way, no way to access the B. Then that's the garbage is, because we don't have any way to access the object. Then the garbage collection module, it comes up and then pre those space when the memory space are available memory space are very low, then it will pre any garbage object there. That's how we implement garbage collection. So this is a little bit hint for the previous slide. So hierarchy, class hierarchy. If you have two class type, the one is point, and then this is color point, and then point is parent, color point is child class. You just inherit all things from the parent. the field and xy, and then function draw and d2o here. I'm going to just inherit them, and then add my things, for example, class C here, and then draw. I'm going to modify the draw, not the original draw. So I'm going to my own draw here. But D2O, I'm still using parent. And also I'm going to add rev here. So I can add my function here. So I can have the object in this way. So prefixing layout, the parent field first and then my fields there. And then we are going to also maintain per class method table. So I'm going to have the method table here, and then the object itself, the first field of the object actually pointing to this method table. And then in the method table, I'm going to keep the address of the functions, okay, address of the functions here, so that I can implement virtual functions. I don't explain too much here, but you are going to learn how they are actually working if you want to implement a virtual function in this way. And then for garbage collections, so as I mentioned that when I allocate the object, it's going to be allocated in the heap, and then I'm going to copy the address into the submain, right? The root set in here is probably starting with the local variable in my stack in the activation record, all the local variables, for example, and then callus object, callus local variable 2, or all the global variables. That's going to be root set. From here, I can follow the address. If I just show the address of the one of the object in here, then I can just access it. If it's still available, I can access it. And then in certain object, they can also have the pointer so that they can access different objects like this. So in that way, starting from root set, I can just explore. So I can have the address. I know at certain point of the program runs, I can just follow the pointers so that I can access them. If I can access them, they are still chance to use it. But some object, there's no way to reach to this object. Then this is going to be garbage. For example, once I had the pointers to here, but in the previous programming, when I coming back from the function g, I just lost all the local variables. So some of the root set is gone. So those points are gone. Then this is going to be no way to reach it from the root set. Then this is going to be garbage. Then I can just deallocate this in the garbage collection. Okay. So this is summary slide. So in a programming language course, we are not going to learn a specific programming languages. You have to learn it from different course, or you have to have some of the experience in other courses, lab practice, and then some of the programming project in other course. Once you have some of the knowledge of a few programming languages, you can actually ready to take the programming language, because we are going to try to understand how actually program runs on a computer, and then how special features are implemented in a programming language. Those features in the programming language, how they are actually implemented. So we try to understand how programming languages are translated in a compiler, and then we try to understand some of the special features, in the program languages, and then also try to understand how to implement those features are possible. Okay? That's the goal of the programming language course. So actually, in the programming language course, we are going to cover probably 3 textbooks: compiler, program languages, and computer systems. Probably not all of the chapters in this book. some of them, and then some of them. And also we have the advanced Java programming language and compiler course too. And then in that course we will also cover the chapters we skipped in this course. That we can have to look at those topics in the advanced code too. Okay.